everyone, and welcome to another Math Research Live with me, Charlotte Aten. So I'm happy to finally be back at it. It's been a busy couple weeks, but I finally actually posted the preprint that I was going to post, and now I'd like to finally actually talk about it. After saying that I was going to have something posted for a while, I'm finally ready to discuss it. And so here, maybe I'll pop over here and show you the thing that I have linked in the chat. So this is my current version of this on the archive. So it's higher dimensional book spaces. And this is actually a project that I did. I basically did the math that's in there maybe 6 years ago at this point, back in 2018, when I was still a grad student. And I've now finally actually cleaned it up, and I have a much nicer presentation of it than I did years ago, but I've also finally posted it on the archive. And so I'm pretty excited about that. And I figured that, I already gave a talk about this, which hopefully should be posted soon. I already gave a talk about this for our algebra and logic seminar at Boulder, but I figured that I would do a live stream and I'd just kind of talk about some different related things. I keep learning new things, or in some cases relearning things, since I've been getting back into this since it was a few years ago. I just figured I'd share some things in a slightly more laid back format, where I can just kind of go on and draw pictures and make mistakes, maybe more than I would in a typical seminar format. So if you check it out, go to the link. This is the version that's currently on the archive. I actually expect a new version to be on there pretty soon. There are a couple typos that I definitely have discovered at this point that are corrected. One of the big things is that this should be okay. Maybe it's not that big, because if you're reading it, you would understand the context. But this should actually be the geometric realization of MDN instead of just the thing itself, because it's supposed to be the space. So there's some small things. And a bigger thing is that in my draft that I currently have going on here, let's just give some more room here. We can see that we have okay, no, it's too zoomed out. All right. Just going to mess with this for a minute. One of the big things that I have added in the current version of this thing is I have some pictures that I didn't have before, and so these were in the talk that I gave, and I'll post the slides for that on my website soon. The video of that should be available soon. But yeah, I've got some nice pictures of these lattices, and then I've also got some 3D pictures. I don't know if they're the most clear. I'm kind of uncertain of how I want to ultimately do this, because I think that it's possible given the context. Oh, hey, hello. How's it going? Showing off my 3D pictures here that I made with Tixie, whatever you want to call it. So yeah, I'm thinking maybe I'll label the vertices of these. I kind of feel like maybe I should do this a different way, but I'm not really sure. I mean, I could make the lines dotted in these perhaps, but I don't know. I do feel like there's a certain kind of elegance to just saying, well, it's these particular points and that's what it is. Did you find somebody outside, Davi? He's looking out the window. He's poking around. Well, yeah, so I'm still debating exactly how I want my pictures to be, but I have some pictures. Yeah, but I'm not going to change it too much beyond what it is, because I'm hoping that finally, currently with the pictures, this is 8 pages, just barely 8 pages, but I'm hoping that finally I can have a short paper published, because everything that I write seems to start off long and get even longer in the editing process, which is not, I gather, is not normal. I think normally they end up telling you to take stuff out, but every time they tell me to take stuff out, they ask me to add stuff in, and it's always more stuff than the amount of stuff that was there originally. So, well, that's, yeah, so that's what I have going on. So I figured that I would just maybe talk about this a little bit. I figured I wouldn't give a whole formal talk about it, since I've been talking about topological lattices off and on in the stream for a while, unless somebody just wants to ask or has a question about, a specific thing, and maybe I just talk about the idea a little bit and talk about what I've been thinking about lately. It's kind of the usual stream of consciousness sort of thing. One thing that I'm really pleased about, with this, here maybe I'll show on this one, is that, I mean, this is just like a silly thing, this small thing, but I use the term porism for a geometric proposition. I actually double checked, because I remembered learning this word at some point. It's just some proposition or lemma, but it's geometric. And thinking, I want to have a paper where I use that someday, because it's an antiquated thing that nobody uses this, it's not, it's not really a thing anymore, outside of maybe there are Steiner, there's Steiner's porism, where there's one or two things where it stuck as part of the name, so and so's theorem or whatever, but it just didn't really stick around, and I figured I'll try to use it in this, because I realized that it seemed reasonably appropriate. And then when I looked it up, I saw some differing opinions on precisely what type of geometric proposition it should be in order to be a porism. But then I just figured I can just call it a porism if I want to. I mean, it's not like anyone hardly uses the word anymore anyway, so whatever. I'll just... Oh yeah, thank you. Yeah, I had that other short paper. So this is another short paper from grad school. So my other short paper was last year. I had this thing that I posted that was a formula for the partition numbers, or a formula involving the partition numbers, and it was I don't know. I mean, it was. I thought it was interesting. If you remember, I didn't say who, but somebody fancy, said that it was interesting, and then I submitted it, and I didn't get anywhere. And I'm trying to remember. Did I submit it somewhere else? I submitted it to either one or two places. I think it might have even been two places, and it got rejected both times. So it's no information. I'm pretty sure I submitted it to a second place. But anyway, so then I was okay, well, should I do some, I did a live stream actually where I was okay, I'll try to soup this up somehow, just add on some I've seen this happen, maybe more in other areas than math, but I don't know, I'm sure it happens in math too, that it's okay, if I add on some not strictly necessary generalization or abstraction, then people will find it to be more enticing or theoretical or something, even though people in the area already said it was a good thing on its own. So I don't know. So then I looked at that a little bit, but then I didn't really feel it was worth the energy, and I just kind of fell off of it. So I might try to run it by some more people in that area who I know again, see if there's anything good that can be done with it. I think there was even someone who I talked to one time who said that they might post something that was a follow-up to it, which would be really funny if it never got published, but there was something that was a response to it that did. I'd be oh, okay, great. So I have a citation, but Yeah, I don't know. So I don't know what's going on with that. Still have not gone far enough in the direction of partition stuff in order to like have a more like broad understanding of like what the implications of that are, if anything. I still feel like it's conceivable that some kind of nice formula could come out by using the one that I had obtained and doing something to eliminate or estimate away the Dobby, what's up, buddy? It's okay. It's probably okay. Dobby, leave it. Leave it. It's okay, buddy. It's okay. Other people are just living their lives, bud. They're just living their lives. It's okay. It's okay, bud. I don't know what's going on out there. Alright. Well, anyway. Oh, what are the parameters for a paper to be accepted? Well, you know, it's the usual thing where it's, there's some kind of ostensibly, you know, objective process. Dobby, buddy, leave it. Leave it. You're being too much right now. It's just too much. Those people aren't bothering you. Okay, buddy. Oh, he's just all kinds of all over the place. All right, Dobby. It's okay, bud. Yeah, shake it off. Shake it off. Okay, so, you know, like ostensibly it's an objective thing, right? Because like, you know, we're mathematicians, we're very objective, you know, even more so perhaps in science where, you know, there's measurement errors and, you know, there's empirical things happening and like, you know, nothing's really perfect, you know, in math, like it's, you know, it's objective and rigorous and everything. Except like what actually is happening is that although in principle anything that we do can be like formalized and verified by a machine, that sort of thing, like we could write everything that we do in like first order logic or something like that if you really made us and we took the time to do it. The correctness of the mathematics is not really I mean, like the math should be correct, or at least it should be clear that, you know, it could be made to be correct with, you know, without like an unreasonable amount of work, as in like gaps could be filled in, like that type of thing. But like, you know, the thing that determines whether something gets published, you know, is whether it's like original, whether it's like an interesting contribution to whatever the discussion is in a given area. And so like this can become a highly social thing because, you know, although people can try to give objective arguments for like why their area of math or their particular interest or their particular way of looking at a certain type of problem is like the objectively best one or the objectively most interesting one that should, you know, have more resources dedicated to it, more people looking at it. You know, it's at the end of the day, it is like there is a subjectivity to it. Like math is subject to fashion the same way that science or, you know, fashion or art or anything is. And so that can also have an effect. Oh, and then of course, obviously, the personal aspect of it, you know. Especially if there's only so many people in a given area, right? Like there's not an unlimited amount of people to review your paper, or people or editors of journals and stuff. And so then, you know, I mean, it can go either way, right? Like it could give you an unfair advantage or it could give you an unfair disadvantage. Like if people for whatever reason are personally opposed to getting your, you know, stuff published, then they could potentially stop you. Or if you have like, you know, some personal relationship with like the editors of a journal, then maybe like you'll get an unfair advantage, you know. And so that's you know, another reason why it's important to, you know, have more people in you know, each of these areas and have, you know, have the discipline continue to grow, because otherwise it becomes like very like, you know, like you don't want it to just be the same like 20 people reviewing each other's papers over and over again, right? Like it gets, you know, it'll get stale. So it's good, you know, it's good to keep new people coming in who are actually, you know, hopefully determined to do a good job and be objective and everything. So yeah, I hope that gives some idea. I mean, I'm also relatively new, but I have reviewed papers before, and I haven't been the editor of a journal or anything like that, but I've seen, I think I've seen the different sides of this a little bit, so I do have some idea how it goes at this point. um, yeah, but I'm hoping that because this paper, although it's short, it was the answer to a specific question that someone had, that it's at least got a chance at being published, because it was maybe not the most involved thing, but it was the answer to a natural question, and it did mostly use things that other people had already done before, but I put them together in the appropriate way, and I think it's pretty reasonable, and oh, good morning. Well, it's actually the evening for me, but yeah, good morning. So yeah, so basically what I did in this paper is a higher dimensional version of this result, showing that there are all of these modular but not distributive topological lattices. So I guess, I don't know, does anyone have questions about the topic? I am happy to talk about just like the subject of the paper, but I guess what I was thinking was, I have a couple things that I was thinking about recently, and one of them was that I was asked about whether the natural topological space associated to a lattice gives you a topological lattice, during the talk that I gave about this previously. Yeah, I'm glad that you heard about the stream. I'm glad that this word of mouth is working. Yeah, happy to have more people here. Okay, well, I guess I'll say, unless there's a question, I think I'm going to say something that's not actually directly, it's not actually what's in the preprint, but it's something that I wanted to think about, because I realized that I think I just kind of said something like, oh yeah, I think the natural choice of topology should work, although it's not what I was going to talk about in the talk that I was giving. Dobby, buddy, people are just getting home from work, bud. You don't need to be hassling them. They're okay. I mean, they're probably okay. Who knows, right? Dobby, leave it. Dobby, leave it. All right. I'm gonna have to go send him to the other room if he can't chill out. Dobby, leave it, bud. You gotta. I think you're getting too stressed out. All right. So before I do the thing that I was gonna do, I'm gonna just take Dobby to go cool off for a minute. So I'll be right back. Thank you. I was just saying. Dobby was having too hard of a time with all the people out there, so he's been banished to the other room where he has to suffer being cozy in the blankets or something instead of barking at people out here and being stressed out. Yeah, it's a hard life that he has. So here's one of our favorite lattices, which is usually called N5, and it's the pentagon. I always want to say pentagram, but that's something else. The pentagram is the graph that we usually call K5. It's a complete graph on 5 vertices. But okay, so here's one of our favorite lattices. Oh, well, you know, my partner and I give him we give him lots of attention. You know, we're here a lot, and we play with him, and we take him out, and we go to parks and stuff. You know, I'm not sure. I'm not sure. You know, with our current living situation, I don't think we can handle another animal like Dobby, but we do try to get him, you know, socialize him and have him visit other dogs, you know, at the park and that type of thing, you know. He actually is quite friendly. He just, you know, he wants to defend his home from the strange people who happen to live nearby. Pentagrams are a special case of pentagons. Yeah, they're decorated pentagons. But okay, so if we have this lattice, then we can consider all of the downsets of this lattice. So if so maybe I'll denote it like this. So this lattice we usually call N5. So it's 5. It has 5 elements, and it's not distributive. It's not modular. It's the unique obstruction. Well, yeah, it's the unique obstruction to not being modular. And so if we look at the downsets, these would be all of the, I don't know, I guess I'll say S subsets of N5, such that well, if X is an S, and Y is less than or equal to X, although I guess the equal part is obvious, then Y is also an S. So that's what it means to be a downset. So downsets look like this. They look like things that, you know, if you look at any element below the one that you're currently looking at, it's already in your set. So like something like this would not be a downset because 0 is below something in here, but it's not in the set of things that I circled. So so we can consider all of those possible downsets, and well, you know, there are a bunch of examples. Actually, I can probably even just write them all down. Let's see. So there's the one that just has 0. Oh, actually, I should be even more. Should be do the even more special case first. The empty set works. It's This would be vacuously true for the empty set. The set that just has 0 works. The one that has 0 and A is a possibility. The one that has 0 and B is a possibility. The one that has 0, B, and C is a possibility. You could also have like 0, A, and B. Oh, that's the vertex. That's the vertex 1. Here, I'll make it look more like a 1. And let's see, we have 0A, 0B, 0BC, 0AB, 0ABC. Okay, and then we just have, well, just maybe I'll just say all of N5. And think that's it. See, because I have just this. I could have this. I could have this. Or this. Or I could have all of these together. Or I could just have this. Let's see. Or, yeah, or I could have everything. Okay. So, notice that if we have two different downsets in this lattice, then if I take the intersection of them, well, I mean, the intersection is going to be everything that's in both, and if I take some like x that's in the intersection, and some y that's less than or equal to x, well, we know from this that x is in u. So since y is less than or equal to x, y is in u. And similarly, x is in v, and since y is less than or equal to x, y is in v. So y is in u intersect v. So actually, this is closed undertaking intersections. And if I do unions, well, if I do u union v, I'll try to give my u's a little tail to show that they're u's. If I do u union v, well, if I take some x that's in that and some y that's less than or equal to x, well, either x is in u or x is in v. So suppose that x is in u. Well, then we know that y is less than or equal to x, and u is a downset, so y is actually in u, and so y is in u union v. And similarly, if x was in v instead, then well, it follows that y has to be in v because v is a downset, and so y has to be in u union v. Okay, and so actually from this we can see that the downset, this lattice, is well, actually the downside of just any lattice, I mean, it's the same proof, it's the same argument if we just use any lattice at all, even an infinite one. So the collection of downsets of some lattice was going to be closed under finite intersections and arbitrary unions. You can do the same thing for even an infinite union. So, well, okay, and also, the empty set and the whole set also satisfy this condition for easy reasons, and so, contain. This also contains the empty set and the set of all points L. So yeah, so well, okay, so I guess a couple things first of all. So what I just said here is so that makes the collection of downsets this is a topology on the elements of the lattice. But okay, so there's another comment though, which is always having zero. It reminds you of having subspaces or some kind of normality thing from abstract algebra. So well, I can. There are a couple different connections. So so first of all, these collections of things that are downsets, I mean, they are like sub-algebras in a certain sense of the lattice. They're not sub-lattices because they're not closed under joins. Like for instance, if I look at the collection that has 0, A, and B, if I take the join of A and B, I'll get 1, which is not in my set anymore. But these collections, because they're closed under going down, if you take the meat of two things in this collection, you're going to get something that's below both of them, which definitely has to be in your down set. So this is so it's a sub-meat semi-lattice because of that. So it is like a kind of sub-algebra type of thing, and an ideal. So an ideal in a lattice is actually defined similarly to the notion of an ideal in ring theory. So an ideal is a set of elements which is closed under. So the idea is that the meat is like the multiplication. So an ideal would be a collection of things which is closed under joins and absorbs meats. So that's like saying it's closed under addition and it absorbs multiplication. So ideals are more special than downsets. So this is a downset, but it's not. This is a downset, but it's not an ideal because so it is closed under meats because downsets are okay. So it's closed under meats, but it doesn't. But it's not closed under joins. It's supposed to be closed under joins and absorb meats, like being closed under addition and absorb multiplication. So it's not closed under joins because like A join B is 1 and 1's not in the set. So this is not an ideal. So let's see what can we pick that's an ideal. Let's see. Will this work? So if we have this chain, if I take the join of any two things that are in the chain, I'll just get the biggest thing in the chain. So that that will work. But if I take the meat with something that is, well, of course, if I take the meat of two things, that's in the chain, I'll just get the bottom thing, which is still in the chain. If I take the meat with A, well, oh no, this isn't. That's right. Ideals should be downsets. They should be special kinds of downsets. That's right. So I can't have chains like that because if I did one meet A, I would get A, and that's not in my set. So I guess the question is, are there any downsets here? Oh no, I told you I gave you a downset. Oh, 0 AC 1. Oh yeah. So 0 AC 1 doesn't work either. So actually, that's right. So we have to have a downset. So ideals are special kinds of downsets, basically for the reason I just showed you. That example is like why you can't have, you have to have the elements that are below anything in your ideal be in your ideal. So well, let's see. For these downsets, I showed you an example that was not an ideal. This isn't closed under joins. Let's see what else. Okay, so just zero works. So just 0 is an ideal. I guess you might consider the empty thing to be. You might consider the empty thing to be an ideal, but that's kind of a technicality. I do want it for the topology thing I was talking about, though, because it's I need the empty set to be an open set in my topology. But if I do 0A, well, if I take the join of any two things in here, I'll get either 0 or A. If I take the meet with anything that's outside of it, well, I similarly will get either 0 if I do 0 meet anything, or if I do A meet either of these, I'll get 0, and A meet 1 is A. So this is an ideal. This is a non-trivial ideal. And so actually, there's always, if you take any element, like say C, there's always the principal ideal, and it should be analogous. It is like an analogous thing with the principal ideal of a ring. there's a principal ideal that's determined by the element, which is all the stuff below it. And so that's why the choice that I chose before didn't work, because any ideal that contains 1 would have to have the principal ideal determined by 1, which would just actually be everything below 1. So if I look at all the stuff below C, well, that's closed under joins, and if I meet with A, I'll either be getting 0, or if I do 1 meet something in here, I'll be getting whatever that thing is that I started with. So that's another ideal. Yeah. So, well, there are several because of that, right? There's 0 in A, 0 in B, there's 0 in B and C, and then there's the whole thing. And I think that that's actually everything. So all of those ideals are principal. It is possible to have ideals that are not principal, but in the analogy with a ring, this is like a principal ideal domain where all of the ideals are principal. I mean, we don't call it that in lattice theory, but like that's that's the situation here. So yeah, so that's the analogy. Yeah, you can't the situation of like normality, or like when you can quotient out by something, it's a little bit different in other types of algebraic structures that are different from groups, but or rings, but there is a similar idea, but the general story is that you generally can't quotient out by like something that's like a subgroup or a subring, like something that's like a sub-algebra. It has to be, or even like ideals, I guess, are like, some kind of substructure. Yeah. Unfortunately, it's well, I don't know about unfortunately, but it's not quite that simple. You have to actually think about like what equivalence relations are compatible with the operations, and that's the notion of a congruence in universal algebra. But it's very related to the notion of a normal subgroup or an ideal in a ring, because those determine such equivalence relations. So it's like it is very closely related. So the thing that I wanted to think about was the thing that I wanted to think about here. I mean, of course, just ask as usual if you have other questions. But it was okay. So this down sets give a topology on the lattice, and this just works in general. Like even if I had an infinite union, it would be the same argument for each possible case, and in the end we would still find that the thing below is in the union. So yeah. So down sets give us a topology, and then we can ask if I take a lattice and do the meet and join, and the downset topology, is this a topological lattice? And this is the thing that I had just thought, oh, okay, well, I remember that, continuous maps with respect to the downset topology should be order preserving, and so you would think that, that this should be a topological lattice. But I remembered after I actually gave the talk in which I was asked this question and said this, that I remembered seeing a comment in one of the papers about this type of thing that I was looking at recently that was like, you can't always do this, or it doesn't always work. And so so one thing I've been wanting to think about that I haven't gotten around to yet is what is the situation with this, or without just like looking it up or trying to read more about it, can I figure out what the deal is with this, or at least like look at a small example and see if like it works or it doesn't work. So I guess the first thing that I would want to think about for this is just the thing about continuous maps that I said before. So like, just forget about the lattice operations being continuous, and let's just think about continuous maps between two of these things. So like, suppose that the h from, I don't know, L to, I guess maybe M will be my other lattice, from L to M is continuous with respect to the downset topologies. So okay, so what that means is that given I don't know, given some U in the collection of downsets of M, we have that the preimage of U under H is open in L, which means it's a downset. It's a downset in L. Okay, and so that's saying so if U is a downset in M, so in other words, if X, so we know that if X is in, I don't want to say this. So okay, so I mean that's what it means to be continuous with respect to this topology, right? And so I guess what I want to say is what does that tell me? What does that tell me about the order? Well, I guess suppose X is less than or equal to Y in L. So, well, what can I do? I can consider the downset of H of Y. Oh, I guess I've been doing Y less than or equal to X, so maybe I'll try to be consistent with the notation I was using before. Why not? So suppose that Y is below X. I can consider the downset of H of X. And then, well, what do I know? I know that if I have some downset in M, that if I look at the preimage of that thing under H, then that's going to be a downset of L. But well, if I look at H of X and all the stuff below it, and then I look at the preimage of it under H, I definitely know that X is in this. So I know that because of that, I know that Y is less than or equal to X. So I know that Y is in the preimage of the downset of H of X. Okay, but what does that mean? That means that H of Y is in the downset of H of X, which means that H of Y is less than or equal to H of X. And so in other words, if I have a continuous map with respect to this downset topology, then it has to be isotone. It has to be order preserving. If I take some pair where Y is below X in L, then H of Y has to be below H of X in M. So any continuous map with respect to these topologies is order preserving. On the other hand, if I had an order preserving map, then I think I can also show that it has to be continuous. So suppose the same kind of map H is isotone. So in other words, Y less than or equal to X implies H of Y is less than or equal to H of X. Okay, well, so then if I look at let U be some thing in the downset, in the collection of downsets of M. Yeah, this is a nice example of a topology. So topology captures order. Actually, in several ways, it captures order very well. Yeah, but okay. So if I have some downset, on the other hand, then what do we want to show? We want to show that the preimage of this is actually itself an open set in L, which means it's a downset in L. So I want to show that I have a downset in L. Well, let X be something that's in H inverse of U. The preimage of U under H. I mean, H is not invertible in general. This wouldn't be as interesting if we restricted ourselves to that case. So suppose H is in the preimage of U under H. Well, that means that H of X is in U if Y is less than or equal to X. Well, what do we know? Then we're assuming that H is isotone. So if Y is less than or equal to X, then H of Y is less than or equal to H of X. Since H of X is in this downset, we know that H of Y has to be in this downset as well, because U is a downset. So H of Y is below H of X, so H of Y is in U. And so, well, what does that mean? That means that Y is something that's in the preimage of U under H. But then what we just showed is that if I take something that's in the preimage of U under H and I look at something that's below it, then it has to actually be in the preimage of U under H. So that means that thus the preimage of U under H is a downset in the first lattice L, but that's what it means to be an open set. So the preimage of an open set in M is an open set in L, and so that means H is continuous with respect to those topologies. So H is continuous with respect to the downset topologies if and only if H is isotone, if and only if it's order preserving. So because of that, what that means is that we actually have an embedding of the category of lattices into the category of topological spaces in this way, because we have some way of sending each lattice to a topological space, and the order preserving maps get taken to the continuous maps, and it's not too hard to check that all of the appropriate conditions hold, because we're actually using the same exact function for the continuous map as for the order preserving one, so this respects composition and all of that. So in that sense, studying lattices is actually like studying a special, it's already like studying a special case of topology, actually, because you can think of them as topological spaces, and like the morphisms between them are like continuous maps. And so, in that sense, it is really, subsumed by topology. But, before you go thinking, well, I guess I don't need to study lattices then, I'll just study topology, aside from being good examples, the way that this type of thing usually goes is that things tend to subsume each other in both directions. So there's no true, one underlying thing necessarily. You can use anything to kind of describe anything else in a number of interesting ways usually, and so it's, you can also use lattices to generalize topology in various ways, and so it's neither one necessarily overtakes the other one. They just have interesting relationships with each other like this. Yeah. Okay. So that's the observation that I recalled when I was asked about this thing. Um, but then the question is actually if I take a lattice and I stick on the downset topology, is this a topological lattice? Well, part of asking that question would then be, is the meet operation from L squared to L, but category theory is actually you can view category theory as being like a special kind of structure that you might study in either graph theory, because categories are directed graphs with some additional extra information attached to them, or you could also think of categories as being a kind of partial algebraic structure. So category theory is actually, in this sense, a special case of algebra, or abstract algebra. Or if you wanted to, you could identify categories with their nerves, and you could say, well, categories are really certain kinds of simplicial sets, or certain kinds of, if you think about their geometric realizations, topological spaces. So there's not really like necessarily a single thing that absorbs all the other things. Of course, some of those identifications that I said, you could say, well, you could think about those in terms of category theory, but I mean, it's the same kind of comments keep applying. It's like, yeah, you could think about the identification of categories with certain kinds of spaces as being like a functor, and that's a category theory thing. But then the other perspective, that's a space perspective, is that that's just a way of embedding a certain kind of space into another kind of space. And so, category theory, in terms of like its like marketing, has the category theory in terms of its marketing kind of has the monopoly on this type of like meta thing, but it's not like it's not like necessarily inherently like that. It's like there is a bit of culture to it. I agree, it's really cool, and like it's very well suited to like these kinds of meta type of things, but it's kind of like how in geometry people will study moduli spaces that are like spaces whose points represent other kinds of objects, like curves or other spaces or whatever, and like that's like this sort of meta thing where you say, oh, I have this shape, but it's not really just this shape, it's actually like each point of this is actually itself, like some type of curve or something, and like there's like some kind of algebra on this actually, and I can like combine these things, and and it's like very meta, right? Because like it means that this is an abstraction whose points are other mathematical objects. But like you can just keep playing this game forever. Like you can just keep making a mathematical object whose components are made of other types of mathematical objects, and I like category theory a lot, but I don't think it has a complete monopoly on that. Like these general kinds of things just kind of keep happening over and over and over again. And really, I would say, to me, I think that's like a big part of what the whole business of doing math is, right? Is that you want to find the interesting ways of making these things from other things and understanding how they're related to each other. And everyone's going to have their own perspective that's like more suited to the techniques that they're better at, that they like better, or whatever. But it's not like any one of them really has to win. I mean, maybe people want theirs to win somehow socially so that they can have more students or more money or whatever. But like these things just kind of exist and interact with each other. And I have a much more friendly perspective as far as that goes. That they should all just kind of do their thing together. But I do agree that category theory definitely feels pretty encompassing in this type of meta kind of thing. Yeah, but I think at least some of it's marketing. I really do. because like, yeah, category theory was sold to me at first as a meta thing. It wasn't, it was sold to me as like the math for doing math. It wasn't sold to me as like, oh, like there's this cool algebra that you can do if you give directed graphs a certain like kind of multiplication or whatever. Like if somebody had said that to me and only shown me like, examples that were like very like concrete, then like, I might not have had the same philosophy about it, I don't know. Anyway, I guess that's enough ranting about what category theory means, or, what its role is. But so the question here would be: is the meet operation continuous with respect to? Well, L squared has to have the product topology. So this is going to have to be the product topology, which I guess we'll just write like that. So that's the question. And so remember, the product topology is supposed to be like the most it's like the optimal choice of topology, which makes the projection maps continuous maps. So just like when you're looking at the product topology, like on R2 coming from R, you can make these open sets that are like the product of two open sets from the original thing. So in this case, like, we could take the product of two different down sets from L and get an open set, but we would also like to get other open sets that we could obtain by taking intersections or taking unions of those things as well. Okay. So the question is this going to be continuous? Well, oh, yeah, I mean, it's I hope that some of that stuff that I said was helpful in thinking about these things, because I mean, it's not really an all or nothing kind of thing. Like there's no reason that you have to say, oh, I either completely reject this area of math, or I'm going to just do everything in terms of it and not believe in anything else. You are free to use as much of it. I mean, obviously, if you're like a student and your advisor's like, I really want you to do this, it might be a different story. But like, in life in general, like you can choose how much of it that you think you want to use, and like, sometimes it will be the correct thing to use, but like you don't have to be, yeah, you don't have to completely devote yourself to it just to use it a little bit. Okay, thanks. Okay, I'm preaching the choir here. All right. Okay, so all right. So the question is this continuous with respect to these topologies? And so the thing is, then we need, in order for that to be true, we need that the set of all xy in L squared with the property that x meet y is in U for some downset U. So that would be the preimage of the downset U, which is an open set under the meet operation. We need that thing. Trying to finish writing my curly brace and it's not cooperating with me. We need that thing is okay. Yeah, I thought that the laughing was at the advisor comment. Yeah, I mean, even later on in life, you may have like, you're trying to get a grant or trying to get a particular job or something, and you want to like fit into where it would be best to fit in for some other reason. So maybe you're never totally in control of it, but you have a lot more freedom when you're doing your own thing. Okay, so if we need that these sets are open in the product topology, which I was just denoting like this, although again it's not really just literally all the things that are products of pairs of downsets, but are open in this product topology for each u that is a downset of L. Okay, so that's what we would need to be true. And from what I kind of vaguely remembered in the comment that I remember seeing before, I think that this is not always true now, even though I made noises making it sound like maybe I thought it was because of the previous thing about continuity. Well, okay, so let's think about this for a minute. Okay, well, I guess here's the first thing to ask. So you know what would help us understand the continuous maps between these a lot better would be if we could understand is the product topology here the same thing as the downset topology for L squared, right? Because there's actually two different possible things that we could have here. And so if it was, right, so in other words, so if the downset topology on L squared, there's such a lattice, is actually the same as what I had denoted like this, the product topology, then the meet operation from L squared to L is continuous if and only if it is isotone, if and only if it is order preserving. And so that's an easier condition to check, because then I just say, okay, maybe I have ZW is less than or equal to XY in L squared, and that just means Z is less than or equal to X in L, W is less than or equal to X in L. And then, well, is Z meet W less than or equal to X meet Y? That would be asking if that map is isotone. Well, if here's your X and here's your Y, and then Z and W, well, I have X meet Y, and then, well, if I did Z meet Y, Z is less than or equal to X, so Z meet Y would have to be like somewhere down here. It'd have to be below X meet Y. So maybe that's the thing I want to draw. So Z meet Y would have to be below X meet Y. But then, well, Z meet W. So if I did Z meet W, okay, maybe I'll just write out what I'm saying. So if I have X meet Y, that has to be at least as big as Z meet Y, because Z is smaller than X. And then, well, if I look at Z meet Y meet W, that has to be even smaller, because I'm taking the meet with something else. But then Y meet W, well, W is below Y. So that means that must be even smaller, and that is actually the same thing as Z meet W. So that's true. So the answer to that is yes. Okay. So okay. So that means that if it was the case that the downset topology on L squared was the same as the product topology from L with itself, under the downset topology, then we would be okay. So if what I'm remembering is correct, since I didn't actually bother to look it up in more detail, I thought I'd just figure it out myself, just as a good exercise for something to do, and because it might be interesting to watch. I'm sure maybe not this whole thing, but at least the first part is definitely an exercise in lots of textbooks that have to do with lattice theory. But you know, I figured that, okay, so now what I'm figuring is that if this is all good, then what's going to happen is that this equality only holds sometimes and not at others, and so yeah, so we can probably try to start figuring out when it holds. Yeah, so I guess if I think about what this is saying that every downset on L squared would have to actually just be, well, okay, not literally the product of two downsets, but it would have to be able to be written like as a union of finite intersections of downsets of L. Oh no, sorry, not downsets of L, but the product ones that are like our basic ones. So let's maybe just try to figure out an example. Maybe I'll just even do a smaller example. I'll do the smallest possible example. What about that? That's usually the right place to start. Okay, if I start with a trivial lattice, it's going to be really boring, so let's not do that one. Let's do the lattice that has two things, which are a top and a bottom element. So here's 0 and 1. So this is my lattice L. L squared has 0, 0. I guess 0, 1, 1, 0, and 1, 1. So I guess the question is the downset topology the one that you get by taking the product topology from this? And so yeah, I mean, I guess what I should do if I want to do this explicitly is I should say, okay, what are the downsets from L? They're the empty set, the one that has just 0, the one that has, and then the one that has everything. Oh, I guess notice that makes this like this finite topological space where this is like a nice like example where you have like a closed point and then you have an open point. It's kind of a standard example. And so oh yeah, and also notice like, you know, these things aren't you know, these things aren't going to necessarily these are going to be somewhat unfamiliar topological spaces. Like you're not going to have a lot of the usual separation properties with these things necessarily. Like I can't find two different open sets in that thing I just drew, that one of which contains 0 and one of which contains 1, such that they don't intersect with each other at all, right? Like that's not possible. Okay, so that's what the downsets of L look like. And so then the downsets of L squared are going to be the empty set, the one that has 0, 0, 0, 0, and 0, 1, 1, 0, 0, 0, and 1, 0, and then also the whole thing. Just say L squared. Okay, so then the question is, what does this product topology have in it? Well, certainly it has all things which are products of downsets from L. So we certainly have, okay, the product of the empty set with anything is just the empty set, so we still have that. If I do 0 with itself, I'm just going to get the one that has 0, 0. If I do 0 with L, then I'm going to get everything that has say the first entry is 0 and the second entry can be anything. Okay, so first entry is 0, second entry is anything. That's this. And then I can get, similarly, I can get second entry is 0, first entry is anything. So that would still give me 0, 0, and 1, 0. And then I can also get the product of L with itself, which is just L squared. And then I can also take unions and intersections, finite intersections, but everything's finite anyway. Well, the intersections aren't going to give me anything interesting. Oh, but if I take unions, right, the union of two open sets is supposed to be an open set, but that means that this, this is actually going to be, if I take the union of this one and this one, I have 0, 0, 0, 1, and 1, 0. And actually taking unions, I think, will give me anything else. Normal intersections. Okay, so that's what it is. All right, so it's actually that this product topology is finer. It has more open sets in it. So they're not the same. Okay, so they're actually not the same. They're not the same topology, because I should be able to have open sets which are products of open sets in the original thing. So I can do 0 and L, I can do L and 0, and I get these open sets, but then their union's supposed to be an open set, but that's not a oh no, I just missed one. I'm being ridiculous. It is a down set. It's not an ideal, but it is a down set. I just missed one. Okay, no, that's fine. All right, good. I thought, like, at least this example should actually work, right? Like, it seems like it's so close. I was just mistaken. Okay. That's a downset too. And that's it. That's all. Those are all the possibilities. Because anyway, it's the union of those two, and those are already in the original thing. Okay, good. So that's L squared. I was just mistaken. Okay. Yeah, so it's, I thought we wouldn't run into problems this soon. This is the smallest one. Okay, now I think I'm good, because downset should be this, 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 all three of these, and then the whole thing. Okay, good. And if I do the product topology, okay, well now if I do the product of this, okay, I guess okay, now I should be careful now that I already made one mistake. Let me be more careful. So if I do the product of this thing, oh no, not this thing. Oh, it's just back up here. Oh no, so I did what I was supposed to. Okay, I'm all good now. Yeah, so I did all the possible products of things from downsets of L. I made all this stuff. I took the union of two of them and I got this, which also, even though it's not like a product of two basis, two open sets from the original thing, it's still, it still should be open, and this is also open in L squared. Okay, so these are equal. All right, good. So, okay, so it looks like barring any other kind of error here, it looks like that equality actually holds. Okay, but that means, by what I just said, what I said before, that means actually that in this case, oh, and basically the same thing applies to joints as applies to meets. This is, in this case, actually a topological lattice that is finite, and its topology is like that topology with the closed point and the open point. So that seems like that should actually work. Because, and it's just because the product topology in this case looks like it turns out to be the topology L squared, and so because of that I can just check if I have an isotone map from L squared to L instead of checking continuity directly, and so then I see that it has to be continuous by the previous thing. So okay, so like there are examples. It's not like you can't get any examples this way. I should have mentioned this in my talk, but I guess I just wasn't thinking about it because the examples I wanted were like things that were like nice, like Hausdorff spaces and everything. But I suppose even if I had thought of it, I might have avoided mentioning it just because of the possibility that, at least at the moment, I'm still under the impression that it's possible to have this fail. Okay, so now let me think about this. So this example should hopefully help us to understand if it's true in general or when it would fail. So what happened here was that when I got my open sets for the product topology, what was happening was I was taking an open set in L, which is like a down set, and then I was taking the product with just all of L, and so that would give me something like this, which was a down set, and then just it had just like some coordinate added on, some other, like whatever other coordinates added on, and that would give me a down set. So trying to think, because like, okay, if it was going to fail, I'm not seeing yet why it would have to always work that these are the same, or why it would be possible for them to be different. So I guess like there are downsets in L squared that are not the product of two downsets from L. That's like this thing that had tripped me up before. So it happens that this thing can be written as the union of two downsets in L squared that are a product of a thing from L and a product and a product with another thing in L. So I guess the question would be, can you find a downset which cannot be written in this manner? In L squared, because like what I'm thinking is like maybe I could just take each element of L squared. Maybe I could just take each thing that was in L squared. What would be the isotone? Oh, so the reason that this is continuous, that these are continuous, is because, oh, I guess I didn't need a whole new page, but back up here I said, oh, like what would make meat continuous, or what would make it isotone? So what would make it isotone is if you had some ZW that was less than or equal to XY. So that's like something in L squared that lies below something else in L squared. Then is the meat applied to the smaller thing less than or equal to the meat applied to the bigger thing? And the answer is yes, and so that means that meat is order preserving from L squared to L. But the fact that it's order preserving, if these topologies were the same topology, because of the thing about the downside topology from before, the isotone maps are exactly the continuous ones with respect to that topology, that would show that this was actually a continuous map with respect to the downside topology. And the same exact type of argument applies to the join also. You can do the same kind of calculation and see that the join has to be an isotone map as well. So yeah, yeah, sorry, I was just thinking about something that was not it was a meta thing that I think I don't want to go into right now, but that's okay, well maybe I will. I'll do an aside, right? It's my stream. I can do whatever I want. I mean, within reason, you know. Twitch have mercy on me, right? I'm not doing anything questionable here. But all right, so here's an aside thing. If you know, so what I observed a minute ago was that so the meet and join. So if I just have some lattice, meet the meet operation from L squared to L, and the join operation from L squared to L. These are isotone. These are order preserving. And so, oh no, I realize what I'm thinking. Okay, so they're order preserving, but they're order preserving, but that doesn't mean that they necessarily preserve meets and joins. That's right. So like, just to give an example, just because you have an order preserving map between lattices, it doesn't necessarily mean that it has to preserve meets and joins, because if I map this to the chain like this, these are both lattices, but say this is F that does the indicated thing. A meet B is equal to 0, but and so f of A meet B is f of 0, 0. F of A meet f of B over here is going to be A meet B, which over here is A. On this side is A. I'm just using the same letters just to make it easier. Maybe it makes it more confusing, I don't know. But so A meet B is A, and so f of A meet B is not the same as f of A meet f of B, and so this is not a lattice homomorphism. The fact that this is not equal to this means this is not a lattice homomorphism. It doesn't preserve the lattice operations. It is order preserving, but it doesn't preserve the lattice operations. So anyway, the reason I thought of this is I was thinking, if the meet and join actually did preserve the lattice operations, that would be interesting, because it would be like, it would be like that you had like a lattice object in the category of lattices. But I don't think that's necessarily true in general, but I kind of want to check just because it seems like an interesting thing. So saying that the meet and join operations are actually lattice operations is saying that, or lattice homomorphisms is saying that that if you took I don't know, x1 y1 and let me think about what I'm saying here. So what would it mean for the meet operation from L squared to L to be a lattice homomorphism? It would mean that either we could take the meet of two things in L squared, so that would be like x1 y1 x1 y1 x2 y2. So we could take the meet of two things in L squared and then apply, I'll just put it on the outside. I know that's a little bit evil to use the infix and prefix notation in the same expression, but you can either do it that way. So take the meet of two things in L squared and then take the meet of the resulting things. And so if we did it this way, we would get that we'd want to take the meet of the pair of things that we got, which was, the meets are done component-wise here, so it's x1 meet x2, y1 meet y2, and then when we take the meet of these two things, we would get x1 meet x2 meet y1 meet y2. And then similarly, so that's one way to do it. Or we could do the meet operation first to send. Okay, they're both a meet. Sorry, I should have used a different symbol, but we should. Or we could do it the other way around, where we first apply the outside thing. So in other words, we first do like the outside meet. That's like the meet of x1. Sorry, not x2. y1 to send it over to L, and then we take the meet with what we do if we did this to x2, y2, and so then in this case we would get x1 meet y1, and then in L meet x2 meet y2, and that those are equal. These two things are actually equal by the. These two things are actually equal by the lattice axioms. Because the meet is associative and it's commutative, and so you can just twiddle these around. Okay, so that means that actually, okay, so that is a lattice. That is actually a lattice homomorphism. It's more than a continuous map. It's a lattice homomorphism, and so that means that. I don't think I ever noticed this before. I don't remember ever thinking about this before. But the reason that that's interesting is like that's like saying that like if you start off with a lattice, the meet and join operation that you get are actually themselves lattice homomorphisms from L squared to L. So every lattice is actually also a lattice object in the category of lattices, and that's like this weird kind of like meta thing that I think doesn't always have to happen for algebraic structures. Like for instance, like what would the analogous thing be like for groups? Like, you know, what would it mean if this were to happen for groups? It would mean that like the multiplication map, if I did the multiplication map from like g squared to g, that would have to be a homomorphism. That would be like saying, okay, well basically the calculation I just did, but I'll do stars instead of meets. So what would that be like saying? That would be like saying if we did it this way, we get x1 here. Okay, maybe I'll drop the stars. We get x1, x2, y1, y2. But if we did it the other way, then we get like the analog of this expression, which would be x1, y1, x2, y2, and so this. Okay, so yeah, so like this is only true for abelian groups. So that's the thing, is that this kind of like, and we'd also need that the inversion, if we were really going to do this carefully, we'd also need that the inversion was a homomorphism, which would again tell us the same thing. And that, well, okay, the identity is a homomorphism in a degenerate way, so that's fine. So like lattices have this property in common with abelian groups, that like an abelian group is actually an abelian group object inside of the category of abelian groups. That's like this like meta, this is sort of meta thing, like categorically. And lattices have this as well, that like lattices are lattice objects inside of the category of lattices. But that's not true for groups in general. Groups in general are not group objects in the category of groups. It's more special. You know, the groups that have that are the abelian groups. They're more special. Okay, so okay, so what do you mean by abelian algebra, I guess, is the question. So if you just mean that the operations are all commutative, then I think that the answer is no, but I don't have I don't have an example instantaneously off the top of my head, but I would be quite surprised if the answer was yes. There is another meaning of abelian algebra, which it's less likely that you would guess, but I mean, I don't know, you're watching my live stream, so like maybe you're aware of these things. But there's also like abelian in the sense of universal algebra. Yeah, I meant like did you mean abelian in the sense of like abelian categories? Maybe. I mean, there though, it's like you're already assuming that everything acts like an abelian group, so, or a module or something. So it's like not, it's kind of begging the question, I guess. But yeah. So I don't have an example, but in the case of where all just some algebraic thing where all the operations are commutative, I think there's probably an example that shows that this doesn't have to happen. Because okay, well, I guess what am I saying here? So like, okay, what I just oh, sorry, there's a little bit of a lag, so I'm not sure what the yes it was. If the yes was okay, I'm not sure 100% what the yes was to, but I think it may have been to me saying where all the operations are commutative. Okay, so now since we've gone down this road, I guess what did I just observe? I observed that if you have some operation, if you have some okay, so this isn't what I had intended to do, but whatever. I took us off on this tangent. Let's go with it. So if I have an algebra A and it has a binary operation F, so in other words, if I have a magma, let's just start there, right? If I have a magma and it is actually a magma object in its own category, then like that means that F should be a homomorphism from A squared to itself. And so that should mean, like just like what I wrote up here, that if I do F, like the way that F works on A squared to F of x1, y1, x2, y2, so if I do that on the square to combine them, and then I apply the usual operation F, if I do it this way, I'll end up getting F of x1, x2, F of y1, y2. But if I do it the other way, instead, then I could do, then I would do F in like the single copy, and then over here I'm doing F to x1, y1, x1, y1, F of x2, y2. Okay, so what I require is that these are the same. So in order for that to be a homomorphism, these actually must be the same. And so yeah, so I mean, I guess the thing that I want to say then is that this condition is called this is the entropic, or it's also called the medial law. Okay. So that's okay. So I guess what it is that if you have a magma, if it's actually a magma object, like with respect to itself, like if it has this like meta sort of thing going on, then it has to be medial or entropic. And so I see what you're saying now, because like, okay, so if you only have binary operations on your algebra and they're all commutative, or even if they're just all entropic, then you will have this meta kind of thing where you will have this like meta sort of thing where it is the operations are homomorphisms from the square to the original thing. The reason that I was hesitant is because if you have other operations of other arities, then I don't think that this has to be true anymore. Because like, okay, for instance, like even if all of your binary operations are commutative, because like for instance, if I say that I have a structure that just has a single unary operation, so in other words, this is like, you might call it like a discrete dynamical system or something. You just have a set with a single operation on it, but you're thinking of it like it's like a structure, you know? Well, in order for this thing in order for F to be a homomorphism, that's equivalent to saying that, well, okay, no, that's actually trivial, sorry, because then that's just saying that F composed with F of X is equal to F composed with F of X. Okay, so that always happens. Yeah, I guess that's what I would need for unary. And then I suppose it would obey all the same axioms. And so, okay, so I guess then for zero area it wouldn't be interesting. Oh, let's double check. Okay, so for zero area, what would the condition be for it to actually be a homomorphism? It would be that I have a map from just a zero element set, just a single point, to A. So in other words, I have a constant. What does it mean for this to be a homomorphism from like the singleton thing to A? It means that I can either do F on the singleton thing, which just does nothing, and then I can send it to A, or I can send it to A, and then, oh, but I have to compose with a 0 to, okay, this is a degenerate thing that I don't want to write out the details of, but this also works. So I guess my apprehension comes from things that are maybe like this, that are higher arity. So then the analogous thing would be that like I can either multiply I can have this triple that's like x1, y1, z1, and I can multiply that by x2, y2, z2, like in the cube, and then I can apply the multiplication outside. So I would go from like that to oh no, I need 3 of them, that's right. Yeah, this is going to start to get a little bit messier. There's going to be a higher error. Okay, let me just say it this way, I guess. If people really want to see me write out the axiom, then I can, but there's going to be like a higher arity analog of the entropic of the medial law is what it's going to be. There's going to be like a ternary version of this law, and so in order to have it, if you had any higher arity operations, it would have to satisfy this as well. Okay, all right. So I'm sold on this. Actually, I can't believe I don't remember actually doing this exercise before, but like this is actually very natural. So the algebras that are like algebra objects of the same type in their own category are the things that are like the medial things. So commutative is a special case of it, but in general it doesn't have to be well, okay, I should say commutative and associative. So for non-associative things, being entropic isn't the same thing as being able to satisfy as being commutative. So like for groups, I don't need any brackets here, but in general I do. So like in general, I need this bracket, like I need this bracketing. So like from this I can't deduce in a general magma that x2, that f of x2 y1 is equal to f of y1 x2. That won't work. So like I really do need exactly this. So commutative isn't strong enough. Oh, okay, there we go. So I was right the first time. Commutative isn't strong enough. I can have something that's commutative but not associative, and it will not have this property. That's possible. In fact, I think I can actually give you an example. I think I can give you an example of something that is commutative but doesn't have this property. So if I want something that's commutative but not associative, I don't know. Let's say what if I do the easiest thing that I can and take Z2 and I do this star operation where x star y is x plus y plus 1. Let's see. I think that won't be associative. No, it will. No. What am I thinking? You take a regular tetrahedron in hyperbolic space and augment. I actually don't know hyperbolic geometry enough to know about what ideal things in hyperbolic space are. I'm sorry, but it sounds cool. I don't know enough about hyperbolic geometry to know about that. But yeah, it's like you definitely in Euclidean space. In Euclidean space, we don't. Yeah, in Euclidean space, you can't take a tetrahedron and. Well, okay, I guess I need to be sure what you mean by augment, but yeah, a cube isn't just made by taking some tetrahedrons, sticking them together, and in any like supernatural way, I suppose. I mean, yeah. Okay, so I think I can give an example. Of this. So I want something that's commutative, but not associative. Here, maybe let me do Z mod 3 so I can have enough room to do something else. Let's see. What if I do x? No, because I need it to be commutative. I feel like I should be able to give a nice example. Oh, I know the cute kind of example that I can give. That's all right. Consider the magma with this operation. This is an old thing that's commutative but not associative that I've written a paper about before. It's the rock paper scissors magma. So let's see. Rock beats scissors. Paper beats rock. Scissors beats paper. This is commutative, but it's not associative. I think if I do rock and paper, then I'll get paper, and then paper and scissors will give me scissors. But if I do paper and scissors, then I'll get scissors, and rock and scissors gives me rock. Okay, so this is commutative, but not associative. Okay, so if this is my operation, it's funny that I didn't actually have to invent anything new. I just had to remember the correct thing that I already knew what it was. So if I take this operation, the rock, paper, scissors operation, this is commutative. It's a commutative binary operation. But I don't think that entropic law has to hold. And so in order to check this, I'm just going to make some arbitrary choices. Let's look at rock, paper, I don't know, scissors, rock. Let's try this one. I don't really know for sure, but let's just see what happens. So paper beats rock, rock beats scissors, paper beats rock, so that's paper. On the other hand, if I do rock, scissors, paper, rock, then I get rock and scissors, so rock wins. And then paper and rock, paper wins. Rock and paper, paper wins. Yeah. Okay, so this one wasn't an example, but that doesn't prove that it doesn't work. Maybe I just had to make a different choice. So instead of making that, rock, let's make it paper. Let's see what happens if it's paper. So okay, so paper beats rock, scissors beats paper, scissors beats paper. So rock beats scissors, and then we have paper, and paper beats rock. Yeah, okay. Okay, so let's just double check really quick, but paper beats rock, so we get paper. Scissors beats paper, so we get scissors. Scissors beat paper, so we get scissors. And then rock smashes scissors, we get rock, paper and paper, and then paper beats rock. Okay. Yep. So the entropic law doesn't hold for this. Okay. So that means that's just an example showing that being commutative isn't enough. You specifically have to satisfy the entropic law, which also means you don't have to be commutative either. There are things that are entropic but not commutative. So yeah, the being an algebra in your own category of algebras, that meta property that I just had randomly thought to think about again for some reason, it's the same as satisfying the analog of the entropic law for all possible operations that you have. It's not very interesting if your operation has arity 0 or 1, and it gives you some similar identity that you have to satisfy when your operation has an arity greater than 2, but it's similar. All right, so, yeah. So these are these are cool because they're like well, I don't know. I think it's cool. They're algebra objects in their own category of algebras, and so that generalizes abelian groups, but not groups in general, because non-commutative groups don't do this. Yeah, so that's a fun thing. Now, I suppose if there's no other comments other than thanks for liking the name. So what I found, at least in this example, was that the downset topology on L squared was actually the same as the product topology from L with itself. And so what I would guess is that, if I choose an example that's not like a Boolean algebra like this, but is some less well-behaved lattice, like N5, then I might have a chance of seeing the failure. But I'm not really sure, because I'm still not really sure what causes it to work or not work. I just know that in this case, and probably some other cases that are very similar to it, it will work. But I don't know for sure that, it could be the case that this is always fine for finite lattices, but it doesn't work for infinite ones, for instance. So yeah, I'm not sure yet what the situation is. I guess, is there anything that anyone wants to hear about or wants to know more about? It can have to do with my paper or something else to do with algebra. Oh, Dobby's back, by the way, but he's much better behaved than he was before. He's just kind of chilling out. So that's it's nice. He's just hanging out. He's got his little area over here. I think he used up all his energy barking at people getting home from work. Okay, well. Before I do, okay, so there's two things that I want to try. Oh, it just, I just got a couple things in the chat that didn't come up right away, I think, or just suddenly came up. I'm not sure. Okay, so what should work for polyhedral products? Yeah, I'm not really sure, because I mentioned the thing about the downset topology on this L squared versus the product topology for the downsets, and then I also mentioned the entropic law thing. But in either case, I'm not really sure what the connection to polyhedral products is. Well, okay, just let me know if you would like to elaborate. I'm not 100% sure what the reference is to, but so I'm thinking that I feel like to continue on the theme of what I've been doing, I should check N5 next to see if the downset topology on N5 squared is the same as the downset topology is the same as the product of the downset topology with itself. But I feel like I kind of do want to write down what the ternary version of the medial law is. I don't know if that question makes sense for you're saying polyhedral products just like for like spaces. So I'm only familiar with like, and it has been a while, but I am planning next week, I think, to do that polyhedral products paper that was suggested before. But like, so for spaces, it's like, I'm gonna have like some space is some space is a subspace of another space, and I'll take the product a bunch of times, and I'll use some coordinates to indicate like which components I should be taking. It's been a minute now, but I think I'll be able to remember for next week the thing that I had proven way back when I had first been exposed to this when I was in grad school. So like there's a couple things though. It's like you could ask, I suppose you could ask something like, is there an analogous construction to polyhedral products but for algebraic structures instead of topological spaces? Or maybe to combine the two things together, can I take polyhedral products of topological algebras? But I would need to I see. Yeah, so I think that it's not clear exactly what the connection with polyhedral products will be, but now that I've said that, I am wondering if it's possible to do an analogous construction with algebras or topological algebras. Because if you want to talk about the downsets of a space, you need to have an order, like it should be a lattice or something like that, So like one way of thinking about it, being able to talk about downsets of a space, is to have a topological lattice structure on it. The problem then is that like polyhedral products of spaces can have non-trivial homology, but topological lattices, even though like there are topological lattices that are like the closed interval, between 0 and 1 or whatever, topological lattices have to be homotopically trivial. They can't have interesting homology. So any construction that you could do with them, it either won't actually make another topological lattice in general, or it will always give you something that is not homotopically interesting. It could still be geometrically or algebraically interesting, but like, so I am curious to think about this now. Not that I need another thing to think about, but that's always how it goes. Now I'm curious if how general the polyhedral products construction can be made. Okay, but I think I want to see the ternary version of the medial law. Oh, and I realize the way to write it now. Yes. Okay, I feel good about this. So okay, maybe I'll actually just erase this too, and then, okay. So one way to think about this is that the binary medial law is like saying you have x1, y1, x2, y2, and you can either multiply them together. this way, oh, x2, y2, and then you can combine them to get x1, y1, x2, y2, or you can multiply this way and get x1, x2, y1, y2, and then you can combine them together and get that, and that those are supposed to be the same. That's what the binary medial law is. So the ternary medial law can be produced in an analogous fashion, and so I should be able to say x1, y1, z1, x2, y2, z2, x3, y3, z3, and so if I go this way and then I combine together, I should get x1, y1, z1, x2, y2, z2. Oh, there's no commas. I'm meaning this to be a multiplication. Oh, no, that's right. I thought my 1 was a comma. Okay. x1, y1, z1, x2, y2, z2, x3, y3, z3. And on the other hand, I can go like this, and if I do it this way, it's saying that, oh, but of course I've seen this before. I know another word for this now. I wasn't thinking about it the same way, but I now realize that I know what this is called already. So f from so an n-ary operation, f satisfies the n-ary entropic law or medial law. Yeah, that's true. The comma could symbolize multiplication. I need some way to keep the difference between tuples and products, and so I'm just going to do it this way. But an n-ary operation satisfies the n-ary entropic law when what we usually say is when f commutes with itself, and that means exactly this. That's actually the more standard terminology. Is it's saying f commutes with itself, and so f commutes with itself exactly when it's a homomorphism for its own structure. That's Oh, so this would be for a single ternary operation, but I now realize that if I wanted, okay, now I should actually be more careful. I've realized something. So what I just said is the situation for a single operation, but when I have two operations, I need that they preserve each other. I need that they commute with each other in order for it to actually be a whatever object in its own category of algebras. So for lattices, I only check that meet and join. Okay, so I only check that meet preserves meet and join preserves join, but I need to check something else in order to see if lattices are actually lattice objects in the category of lattices. And so in other words, I need to see does meet preserve join, or do meet and join commute with each other? And so, well, what that means is that if I have two things in L squared, like x1, y1, and x2, y2, that I should be able to take the join of them and then take the meet of that thing, and then I should be able to get the same result as if I took the meet of the pairs and then took the join. It's not all lattices that do this. So if I take the join, I would get x1 join x2, and then y1 join y2, and so I would get the meet of these, which would be x1 join x2 meet y1 join y2. But on the other hand, meet also, okay, so then I would also have to get the same thing if I took the meet of x1, y1, and then I joined that with the meet of x2, y2. And so in order to have this, I would have to have that, well, x1 meet y1 join x2 meet y2. And so I would have to have that these two things are equal to each other. And so, okay, well, when can I have this? Let's see. So yeah, so it's still like the ordering's still the same as the entropic law, but the operations are different. So let's see. Trying to see what this would imply. Let's see. So if I'm supposed to have this, I guess like what would happen if I had a 0 and I said that x2 was, well, I'm not sure what I want to do to simplify, but my intuition is that this is not a trivial property to have. Let's see. So what I wanted was x1 join x2 meet y1 join y2 is equal to x1 meet y1 join x2 meet y2. And so in order for that to occur, well, see, the thing is, like, I want to just say something about distributivity, but like, okay, let's just suppose that let's say that x2 is equal to x1, just see what happens. So if x2 is equal to x1, then this is saying x1 meet y1 join y2 has to be the same thing as x1 meet y1 join, oh, okay, yeah, that is what I wanted, x1 meet y2. Okay, so such a lattice must be distributive. So x1 meet this join, it's the same thing as the join of the meet of x1 with each of these things. It's like multiplication distributing over addition. But for lattices, having it one way means you have it both ways. So this also implies that, like, the fact that I have this means I also actually must have that x1 join y1 meet y2 is the same thing as x1 join y1 meet x2 join y2. Okay, so okay, and now if I did the analogous thing, I see. If I did the analogous thing the other way for join respecting meet, like the other way around, I just get the same thing but with the meet and join symbols flipped. So okay, I think being distributive, I think, is okay. I think that I should be able to get this from. I think this axiom I should be able to get from distributivity, because if I know that I have something distributive, well, that axiom. If I know that I have something distributive, then x1 join x2 meet this would be the same thing as x1 join x2 meet y1 join x1 join no wait, the meet is the one that's distributing. Okay, I see. Alright, so yeah, x1 join x2 meet y1. Oh yeah, it's distributing over join. Okay, I was correct. So join x1 join x2 meet y2. Okay, so those are the same. And then, well, let's see. I want to say that that's the same as x1 meet y1 join x2 meet y2. Oh, but then I can distribute again. So maybe that's the thing to do. So if I distribute again, I get x1 meet y1 join x2 meet y2 or meet y1 join similarly here x1 meet y2 join x1 meet or x2 meet y2. Okay, so I can unravel it into that. So it's just a join of all the possible pairwise meets. No, but on the other hand, this right hand side would, for the same reasons, be the meet of all the possible pairwise joins. Okay. I am currently uncertain of whether this is equivalent to distributivity. No, I think it has to be. No. I'm uncertain. Okay, it implies distributivity. No, I think that distributive lattices, I think that I think it's impossible to have. I think that if you add any additional axiom onto distributive lattices that isn't just already implied by distributivity, I think that it would have to trivialize it would have to make it the trivial variety. I don't think there can be anything more special within lattices that's than distributive and have it not be trivial. I think that distributive lattices are like minimal in that sense, if I recall correctly. So because of that, okay, if that's true, then that means that this is equivalent to being distributive. And so if I'm correct, then that means that the thing that's analogous to abelian groups is not all lattices, but it would be distributive lattices. Distributive lattices would be distributive lattices would be the lattices that are actually like, they're lattices in the category of lattices. Okay, I'm glad I realized this. Okay, so it's not quite as simple as I had originally thought. If you have a single operation and it just has to commute with itself, then you just have this kind of thing, and you can write that down for any particular operation. But it gets more complicated when you have multiple operations, because you have to see that they preserve each other, and so you get these kinds of identities. And so at first, I'm glad you think this is neat. So at first I thought that just all lattices have this property that's like abelian groups, but I was mistaken because I forgot that meet and join have to preserve each other. And so then once you do that, it looks like distributive lattices are the only lattices that can do this, I believe now. But that it should work for distributive. It should work for distributive lattices. So that's I think that's pretty neat. Because there's not really that much of a reason to think of it this way, but one reason it's interesting is you could ask you could say what's what's a group object in group, but then you could say instead what's a group object in the things that look like group objects in group. maybe okay, this isn't the higher category terminology, but this isn't like the higher category terminology, but you say like, okay, maybe this is like a two group in this scheme, and then the things that are like this would be like three group. Hey, you melted on your bed when you got home. Well, that's the way that some days end for sure. So I could keep doing this forever, and I could ask like, what do all these things look like? But I know what all these things look like if I take an abelian group, because an abelian group would satisfy each of these things. It would be a group object on a group object on a group object forever. Yeah. So like the answer, like this type of thing, I mean, it could be different for different things, right? Like I could ask like things like, what does a lattice object look like in the category of groups? And I might get a different answer. And then if I said like, what does a lattice object look like in that, and so on and so forth, conceivably I could get a different answer. But when you have that the operations of the structure just commute with each other, then it's just you have this at all levels. Like it's like the nicest type in that sense. Yeah, I don't know. I think that's cool. Like, I actually don't know. I don't think I know a word for like algebraic structure where all of the basic operations commute with each other, but I feel like that should have a name, or it should be very nice. That's not what abelian algebra and universal algebra means, or at least I don't know that it's equivalent. I don't think it's equivalent to it. Actually, I don't think it can be equivalent to it, because I think I can come up with an example that's abelian but doesn't satisfy the. Okay, I'm not 100% sure, but I'm pretty sure that it's not the same. Well, commutative is definitely overloaded at this point, but we could call them commutative, but I feel like there should be a word. So in universal algebra, it's not the same as abelian. I don't think in the next 50 minutes I can reasonably do justice to what an abelian algebra is in general. I don't think that I'm old enough to become an adjective. I think that there's like a certain stage that you have to reach before you can become an adjective. And I know that if I ever do, which it's not guaranteed, of course, people will confuse it with Artinian, and they'll be like, is it Artinian or Atenian? And like, what's the difference? But like, that's, I mean, I'll probably be long gone if anyone ever has this problem, so, I don't really have to worry about it, I guess. I suppose if YouTube doesn't manage to dump its whole database at some point in the next few decades, I suppose that this might stick around. But I don't know if it'll help anyone in remembering the difference between those two properties, whatever they are. But yeah, well, I feel good about this. I'm kind of curious, like, what this does for other familiar types. Well, I mean, I guess I basically know. Like, for groups, it looks like it gives me abelian groups. I know what it does for algebras that have a single operation. I think for lattices, this gives me distributive lattices. So I guess, like, I don't know, for semigroups, I would just get entropic semigroups, for instance. I guess for rings, I think for rings this is not interesting. Okay, now I'm curious, so I'm gonna do rings. So for rings, what happens for rings? So if we axiomatize rings as having the addition, the unary inversion, I guess I'll do them in this order. So we have multiplication, addition, unary inversion. I'll say 0 and 1 are constants. I'll do unitable rings. So we need that multiplication commutes with addition, and so we need that if I have two pairs, I can either multiply the pairs to get x1, y1 and x2, y2, and then add them together, and I should get the same thing as if I added the pairs and then multiplied them together. This is already strong. No, wait, I should be careful. Okay, so if I take a pair and multiply it, I should be doing, okay, so one of them's in the square and one of them is not, so I should be doing the entropic type of thing where I get x1 plus x2 and then times y1 plus y2. But okay, this is still quite strong, and so I need to have this, and so if I'm actually in a ring, then that's the same thing as saying that well, that this is equal to x1 y1 plus x2 y2, or well, plus x1 y2 plus x2 y1 plus x2 y2, and then okay, I have x1 y1, I have x2 y2. So it's saying x1 y2 plus x2 y1 is equal to 0. I can just plug in x2 and y1 equals 0, and I can see that x1 y2 must actually just be equal to 0. This is the ring that has a 0 multiplication. For similar reasons, I can plug in 1 for y2 and y1, and I see that x1 plus x2 is equal to 0. And I also see that I could just plug in 0 for x2 and see actually everything's 0. This is just a trivial ring. Rings can't do this. I mean, a non-trivial ring can't do this. So rings won't accept this. Well, I mean, not only is 2, well, okay, yeah, not only is 2 a 0 divisor, but it's just the ring is trivial. It's not even that the multiplication is just 0. The ring is trivial. Like, there's only one element. There can only be one element of this ring. There's no non-trivial ring can satisfy these equations for all choices of x, x1, x2, y1, and y2. It's impossible. Even if it's commutative, it doesn't matter. I didn't use that the ring had a commutative multiplication. It just doesn't matter. It just doesn't work. Rings don't like this. Lattices, I believe, give us distributive lattices when we do this, and groups give us abelian groups when we do this. But I don't think that. Rings don't like this. They're just not happy. They're just not happy with this situation. Let me see what I used actually. So I definitely used that we could cancel. I used associativity also. Yeah, I used associativity. I used some of the properties of 0. So it's possible that there are ring-like structures that have this, but like they can't look that similar to rings, or else they become trivial. Yeah, the ring objects, the rings that are ring objects in the category of rings are not very many. So there may be ring objects in the category of rings, but they can't have the same multiplication as the ring that they're on top of. So like, I didn't write down formally what I meant by this, but what I've been looking at are the like algebra objects in that same category of algebras where the multiplication for the algebra object is the same as its underlying object's multiplication. Like, this is like a special kind of symmetry. So it's possible there are like non-trivial ring objects in the category of rings, but like they can't have the same multiplication as the original ring. Like, they can't have all the same operations as the original ring, or else they're trivial. Yeah, so it doesn't work. It just doesn't work for rings. But we've still seen some examples of things that it works for. So, you know, sometimes things that you think, if you ask for too much structure, sometimes you just get something trivial. So that's the situation. I never did really figure out whether or not what the answer to my original question was. So I know that in this specific case, it looks like the downset topology on L squared is the same as the product topology for the downset from the downsets of L, which meant that I could make a topological lattice that way. Oh, which, by the way, going along with the theme, is a lattice object in the category of topological spaces. But I have reasons to believe that this doesn't always work this way, and that these topologies will be different in general, because otherwise, if this product topology was always the downset topology on L squared, in order to check that I had a continuous map from L squared to L, I would just have to check that it's isotone. And I know that these are isotone. That's how I got off on this tangent about algebra objects in the same category of algebras that you're already in, is because I was thinking about how the meet operation like commutes with itself. But yeah, so whenever we have that, we know that this is true, but I don't think that it's true. Don't think that it's true in general. But I also don't have an example yet. Yeah, my feeling is just basically like it's either that all finite lattices do it and the non-examples are infinite, or it's that there's some small thing like n5 or m3 that it just doesn't work for, and it just doesn't work in general. But I don't know for sure yet which is which. Yeah, so I'm not certain about that. Yeah, I could look it up, but I kind of want to figure it out myself. I don't know if I want to just sit here and try to look it up right now. But I know I've seen comments about it recently, in some of the papers that I've been looking at. I just can't remember specifically which one at the moment. Yeah. Oh, I realized something else too that I was not entirely correct about. So after my previous live stream, I like at the end of my previous live stream, I had figured out more or less a formula for writing the meets in one of those geometric realization topological lattices as in terms of the convex coordinates, which was like harder than just taking the minimum of each of the components. But then I was thinking, oh, I can do the same thing for the join, but I realized that actually wasn't correct. So based on what I did before, I do actually know a formula for the meet for one of these topological lattices in terms of the convex coefficients, but I don't know how to compute the joins in terms of those yet. I'm sure that there's a similar way, but it's not going to be quite as easy. But it was still a bit of a thing to get the formula for the meets, because I had to invert that map that was like, I think I called it T before, that took an element of the lattice to its downset, or to the indicator function of its principal ideal that it determined, and so it was not the prettiest formula. So I would still like to figure out what those things are. I'm not sure if I will be able to do that in the next 40 minutes. I don't know. What do people want to see? My default thing would maybe be to try to do the example for checking if the downset topology on L squared was the same as the product for L. But what I would do is I would do it for N5 instead. Actually, let me go back to where's my N5. I would do it for N5 instead. That's one option. Another option is to do something else or have some other question. But that's what I was thinking about as a next example, to see if I could get any intuition, because I can't yet really see like if it is true in the finite case that the downset topology for L squared is the same as the square of the downset topology, I can't see what the reason is yet. Yeah, so that's one thing I could do. How do people feel? Do we have hearts full of neutrality? Is everything just totally cool, legitimate, just awesome? Oh, Dobby's just sleeping over here. I can't. I'd show you, but I don't want to disturb him. It's not, you know. All right. Well, maybe I will. Maybe I'll think about the N5 example, I suppose. Okay, I guess maybe just intuitively, what does this topology look like? I mean, 0's closed. Well, okay, sorry, open, I guess. But yeah, you know, 0 is open. Maybe I said closed and open the opposite way for the other example with the 2 points, but you know what I mean. One of the points is closed and one of them's open. Yeah, I mean, I could, you know, I could code it. I mean, I don't know if I'd be able to make the most general thing in the next 30 minutes, but it's honestly, for something that's this size, it's almost easier to do it by hand. So I'm not opposed to using such tools to do math. I actually am a proponent of it. I think it's a great thing to do. But for certain things, like if my goal is to try to understand the general situation, if I don't know for sure what the answer will be, and I'm not like totally stuck or feel like I'm out of ideas yet, like I do like to try to do it by hand first, because often doing it by hand like makes me think about what I'm doing, and it often makes me realize what the proof is or what the counterexample would be without explicitly just guessing it. But using computer tools to just randomly, like to just check certain things or randomly try to find a counterexample, it can be very helpful, especially when you're not sure how to start, you're not sure what examples to try looking at, or you know, like you tried and you can't figure anything out and you're stuck. It can be a good way to get you unstuck. But like, you know, yeah, I mean, it's always a trade-off though, because it depends on how much work you have to do to code the thing that you're trying. So like for this, I guess the thing is I would have to figure out what N5 squared looked like, and it has 25 elements. All right, fine. So I guess that I'm I feel like Sage Math has to have probably tools for working with finite topological spaces already. Here, let me see how much. Here, let me just gonna see if I can find something here. Yeah, I should probably just turn the Ko-Fi bot off at some point, because I'm still having fun doing this, and I'll probably continue to try to do it still at some regular interval until I get bored doing live streaming, if that ever happens. But I'm definitely not making money from doing it anymore. But that's okay, because actually I got a lot of support when I really needed it earlier this year, and I was having a hard time getting moved over to start my new job, and so I'm not like super put out by it or anything, you know. I'm thinking that maybe it's not. I don't know. I feel kind of neutral about it, but it's something I think about sometimes. Because I still would do this even if I didn't make money from it, because you know, I am at my new job now, and so I don't need to make money from this, and you know, I am just glad that I was supported when I needed it. Finite simplicial complexes. I think that Sage does not do I think that Sage does not do finite topological spaces, like by default. I'm actually kind of surprised. I guess maybe it's too expensive or something. There's simplicial sets, but I don't really want to have to. I just want to directly compute things in terms of the topology. I don't want to have to. I don't want to have to reformulate it as a simplicial set. I know that it's possible. I don't know. I actually do not. I have never used Magma computer algebra system, which is maybe ironic because I just or well, you know, because I'm the Magma person or whatever. But not many results for Magma computer algebra system contain topology. Yeah, I know that like Magma is like my middle name, but oh, yeah, I think the reason that I've never used Magma is because it is proprietary, I believe, if I remember correctly. Oh, Magma does simplicial homology, but that's it. And I think it's only homology. It doesn't compute the product or anything, it seems like. Well, anyway, I'd rather just write my own thing and then I can post it online and it can be free for everyone, and you know. If I was gonna do anything more seriously, I would contribute to Sage, which I've never actually made a pull request to Sage before, but I have written and posted things for Sage on GitHub before. Although it's been a long time since I've posted anything. I actually probably would like to go back and redo some of that stuff, if anything, because I'm definitely way better now than I was back then. Yeah, it seems like maybe the thing to do would be to do this by hand. So I guess the idea would be, okay, if it didn't work, like if it did work, I would just go through all the downsets, right? And look at all the products and look at their unions and see if I could make everything. So the idea would be that if the corresponding topology didn't give me a topological lattice for N5, then the idea would be that how could they be giving anything to us for free? Yeah, I mean, there's a lot of stuff that's like free through your institution too, but of course the institution has some kind of contract or whatever, and they're trying to get the market, because then, you know, you're not associated to one because you go on, graduate, whatever, and then you gotta pay for it, and like, I don't know. But yeah, I'd just rather support free software, you know, like, especially because it's math. I mean, it's like such a fundamental thing. Like, it's not like some like arcane like CAD software for like doing something with like some proprietary classified engine of some plane or something, right? Like it's doing calculations in topology. Like, that's like, everyone's gonna probably use that for something for the rest of all time. It's like just like having a, you know, it's like a basic functionality that the computer should have. I guess okay, so the thing is, I think I want to try to draw a picture of N5 squared, which will have 25 elements, but I want to try. The idea would be that there would have to be a downset that couldn't be written either as one of those products or as a union of intersections of them. So that would be the idea. Okay, so I will try to draw the picture and see if I can figure it out, and if I can't figure it out, at least I drew some pretty picture, and then we'll see what happens. I wrote so many things today. I never do what I think I'm gonna do. I always do something else. Okay, what does n5 squared look like? Well, maybe way down here, I'll draw a big picture. Way down here, should have 0, 0, 0a, 0b, 0c, 0, 1. Okay, that's what all those things look like. Because if I take the meets and joins, of course, like that specific element is just, you know, the first one just stays 0. Okay, for similar reasons, there's something that looks like, there's something over here that looks like AA, here's A0, here's AB, here's AC, here's A1, and these definitely have this kind of relationship with each other. And, well, okay, let's see. A0 and 0A are actually incomparable, but A0 is bigger than 0, 0. And so, okay, so this actually looks like this. So A0 is bigger than 0, 0, and AA is bigger than 0A for similar reasons. Okay, and similarly I can draw this. So we get like this, this pentagonal prism. This is one piece of it. Okay, that's definitely not a straight line. Okay. Okay. And then similarly, I'll have a chunk over here which looks like a copy of N5, but where it's indexed by like here's BA, here's B0, here's BB, here's BC, here's B1. And then I'll just draw there. It has that same kind of relationship with it, as does this copy of N5 that is the one that's indexed by C. So here's CA, here's C0, that's me. CB, CC, C1, and finally the copy that's up at the top. This picture's just degrading the more that I go on drawing it, but you know, you get the idea. There's the cool pentagonal kind of thing going on here. It's looking more 3D. You can visualize it in your mind's eye, since this is not the best drawing of it. Okay. There. That's what it looks like. It's like that. Okay. So the question is, how could I come up with a downset that cannot be written as a union of downsets that are like product downsets? Okay, well I guess the first thing is, what would a product downset look like? What's an example of what a product downset looks like? Well, if I had 0A, that's a downset. And if I had 0 BC, that's a downset. The product looks like 0, 0, 0A, or sorry, not 0A, 0, 0, 0B, 0C, A0, AB, AC. Okay, so 0, 0, 0A, 0B, 0C, and then A0, AB, AC. So it looks like this, like kind of, oh wait, no, okay, 0, 0, 0B, 0C, A0, AB, AC. So it looks like this kind of, these two, it sort of looks like this, right? It looks like these two kinds of like rectangles that are determined by these two things. Okay, so that's what that product downset looks like. And so if I want something that can't be written like as a union of those, I need okay, so let me think about this. So I need something that doesn't look like a union of these. So it should have like, I see. So it should have like all but one point of, okay, I think I'm starting to see the idea. So if it was going to fail, I would need to have something where it was like I took one of these things and then I removed one of the points from it, but preserved the fact that it was a downset. So like, okay, what happens if I just take these 5 points? 0, 0, 0B, 0C, A0, AB. Well, that's closed under looking at lower things, right? Because if I have A0, the only thing below it is 0, 0. If I have AB, things that are below it are like A0, 0B, and then 0, 0. Okay, and if I have 0B or 0C, the only things that are below it are these things. Okay, so that is a downset in L squared. This is a downset. Okay, so if it was true that it wasn't an open set in the square of the downset topology, then it would have to not be able to be written by taking intersections and unions of the open sets in the product. So like, okay, so here's a product of two things. It contains oh, okay, I have an idea. So if I take an open set, then it should be no. I have to, so if this is a non-example, if the topology is actually not compatible with the operations, then I have to show that I can't write this as a union of intersections of the open sets. So if I intersect open sets that are these product open sets, I can get smaller things, right? Because I can take like 0A product with 0B, and that will get me some of the stuff that's in here. In fact, it'll get me 0, 0, it'll get me 0B, get me A0, it'll get me AB, but it won't get me 0C. Oh, but on the other hand, I could do 0, I could do the product of 0 with 0BC, and that would make 0C along with the other, so that one is a union, that's a union of those two open sets. I'm not sure if I'm going to, I mean, it might just be that this is actually the same as the product topology, so there's nothing, I couldn't find a counterexample. But yeah, I'm not sure. I'm not sure whether or not I can find a finite counterexample still. Anyway, you got to have some fun maybe watching me try to draw the picture. You can imagine what it would look like if I had drawn it more nicely. But this is kind of the limit of my artistic abilities. I'm still not really sure whether there's a finite counterexample or not. I still haven't seen why. I still haven't seen why, what could go wrong, or like why in the finite case even like it would always have to be the same. I'm still not sure. So I'll probably later look up that comment and see if I can figure out why people are saying that. I think another nice thing that's worth mentioning is that this space looks like it's something that should have interesting homotopy from the way I drew the picture, but it's not true. So this is still actually homotopic. This has to be homotopically. Well, okay. I guess what should I say? If the topology is compatible with the lattice operations, it has to be homotopically trivial. Oh, okay. So if it wasn't homotopically trivial, then I would know that actually these things aren't compatible. So if the downset topology on L squared was not homotopic to a point, I guess it's connected, I suppose. Then I would know that it's not. It can't be the same as the product topology, I guess, because if it was, then I would have a topological lattice, and it has to be homotopically trivial. Okay, so like that's one thing that I could do, but my feeling is that that can't be the case. Because it's just that this has got to have the homotopy type of a point. I'm pretty sure. Well, anyway, that's what I was thinking about, but I didn't quite get there. But I did think about some other things related to algebras whose operations all commute with each other that were pretty interesting. And Dobby got up to getting into some trouble today, but it wasn't too bad. He was just kind of borking at people a little bit. So there were people out there doing stuff outside somewhere. He really wants attention now. He's woken up from his nap. Well, what does everyone think? Yeah, how dare those people exist outside of us? I bet he doesn't even know that No, actually, I was going to say I bet he doesn't know that I'm talking to people right now, but he does know, because he'll get jealous sometimes when I'm in meetings. I'm talking to people for a while. He'll want me to give him attention even though he didn't care before. Like, he was just fine doing his own thing before. He'll get jealous that I'm meeting with people on Zoom. Yeah, shake it off, buddy. Dogs just have to shake it off sometimes. Yeah, so for what it's worth, I do actually generally like people, and I usually assume that people like me, even if they don't, because I just think it's not like I think I'm so great or something. I'm just like, yeah, like everything's cool. Like you have to try to convince me. You have to try to convince me like that you're not a fan of me. Like I'm just like, all right, like we're friends, right? Like everything's all good. Yeah, like it's just like I don't think I'm totally obtuse or anything, but it's just like because like sometimes people are shy or like not everyone wears their their heart on their sleeve or whatever. Like people aren't always like telling you what they're all about right away. So like if you have to assume, why not just go through life assuming that people probably think you're all right at least. I mean, it won't hurt as long as you don't think that about someone who like really hates you or something. Anyway, I guess that's enough personal philosophy, I suppose. I think Dobby likes people too, because it's like the classic thing, right? It's like the classic like dogs in the fence kind of thing. Like he'll growl at people from here, but if he was actually like out there with them, he wouldn't do that because he wouldn't want to mess with them. He knows that he's safe here and that he can tell them to stay away from his land like when he's like, you know, safe in here, but he won't actually bother people outside or other dogs. Like, he's just, you know, he's doing the usual thing of the, you know, the Chihuahua that thinks it's really tough when it's like behind the door or whatever, you know. All right, well, let's see. I did this. I didn't actually really talk about the paper at all, I guess, but that's okay. Does anyone have anything else that they'd want to know about? We discovered a number of things today, or rediscovered. I feel like I've thought about the question of algebra objects like in the same category of algebras before. Oh, do you want to know more about rock, paper, scissors? Rock, paper, scissors, as we've now seen, rock, paper, scissors is commutative, but not entropic, and therefore the rock, paper, scissors operation is not a homomorphism for its own structure. So it is not a magma object in the category of magmas. It's a magma object. I mean, every magma is a magma in the category of sets, but it's not a magma in the category of magmas. And it seems, if I'm not mistaken, that distributive lattices are the ones that are lattice objects in the category of lattices. So doing this trick seems to tell you the special cool algebras from that type of algebra, but unfortunately for rings, it tells us that the only special cool one is the trivial one, and so. But I don't dislike rings, but unfortunately this doesn't give us anything for that. For groups it seems to give us abelian groups, and for lattices it gives us distributive lattices, but for rings it just doesn't give us anything. And those are the breaks. Oh, well, here's the thing I can tell you briefly in the last couple minutes here, just to leave you with something. So I've talked about Latin squares or quasi-groups on this stream before. So an entropic quasi-group or Latin square, so one that has that property that its operation is a homomorphism for itself, it commutes with itself, has to be of the form, so it's going to be a star where A is an abelian group, X star Y is, I think it's alpha of X plus beta of Y plus, I don't know, S. Oh, maybe I'll do little a. Where little a is some element of the abelian group, and alpha and beta are endomorphisms. No, I think automorphisms, actually. Yeah, because I mean they can't have a kernel or else. Okay, so are automorphisms. Okay. So that's not supposed to be obvious. This is like, I never remember which names are associated with this theorem, but it's like okay, Bruck is a usual guess. It's like Bruck. I want to say maybe Reiser Murdoch, maybe Murdoch. I want to say Toyota. I don't know. So some three of those names that I probably just listed. Some three of those names that I just listed prove this theorem like almost a century ago or something. And so so actually the quasi groups, the like non-associative groups, if you want to think of them that way, that are entropic, have this property, that they're actually just, they look like twisted abelian groups is what you might say. They're basically given by the abelian group addition. And so there are examples that are not abelian groups, that are entropic. And I suppose that if I choose this, that's the thing. I wanted a commutative example that was not entropic. That's why I did the rock paper scissors thing. So here you can see examples that are entropic but not commutative. That's what it is. Because if you switch x and y, you'll have two different automorphisms in general. Well, maybe that's a good place to call it, unless there's anyone else wants to say or ask anything or anything at all. As always, I had a lot of fun doing this. I feel like I sometimes, just due to people asking questions or just, kind of thinking out loud a little bit more, I think of things that I wouldn't otherwise, or I discover things that I maybe wouldn't otherwise, and I always have fun doing that. So, I'm glad you had fun too. That's a great reason to be here. So next week, I think I'll probably do the polyhedral products paper that was suggested. And, I was kind of trying to do this every single week at this time. In practice, it seems like I usually do it at least twice a month, at the same time on well, it's Monday for me. I don't know what time, I don't know what day it is for you. It depends on your time zone, but, I usually do this once a week on Mondays, but depending on how busy I am or other things going on, it's every Monday with like a asterisk on it. Thanks. I think I'll take a look at that polyhedral products paper. I'll try to remind myself of the calculation that I did related to it when I was in grad school, and I can tell you my story about that because there's a story with it. I'll also think about if polyhedral products make sense for algebraic structures as well, because I had made myself think of that, and I now want to think of in what ways does that make sense for algebra. So it should be pretty cool. I hope that you all have an awesome week, and I hope to be back here next week to talk about a different thing in combinatorial topology. So I hope that you'll join me then. All right, well, have a great week. See ya.